Okay, I think I'll start my lecture. I'll be using this mic because I think this is not charged, so I'll be a bit closer to the screen, and I apologize for that. And the attendance score is 789, 765 for the lecture. I'll write it down as well. Cool. So, good morning, everyone. My name is Bharat, and I'm a postdoc in the Quasar group with Carsten, and I'm based at Darsbury. And my expertise is in beam diagnostics, so I thought of giving this an introductory lecture on beam diagnostics. I'll start with the picture. The picture that you see in this slide is the trap that I work on with collaboration with CERN. It's a penning trap, and we use different kind of diagnostics to identify what kind of particles are there, how to detect them, and so on, and which I'll cover in the coming slides. So this is a bit of my background. I did a PhD on ion sources, which is very much related to particle accelerator, but my application of the ion source was in electric propulsion, so for ion thrusters in space. So I designed and optimized the ion source for a particular application. And currently I do beam transport studies for the development of a digital twin for the antimatter experiment at CERN. So this is the actual trap that we use for confining the antimatter. And I'm making a digital twin, which is a computer model of the exact same thing, which is very challenging because it is computationally very expensive to simulate all the physics processes. And yeah, so let's start. This is just an overview of how this lecture will proceed. I'll introduce what the term beam diagnostic means, what do we measure it, different kind of properties that we measure for a particular application, a particular accelerator, which includes measuring its position, measuring the profile of the beam, charge, current, losses, and different kind of other things. So I'll also cover the real ongoing R&D case studies and some pen and paper calculation, which can be helpful for you to analyze. And at the last, if you have questions, we can discuss everything. So what is beam diagnostics? So beam diagnostics, the word diagnostics, it means to diagnose certain thing. Yeah. So as an analogy, you can understand whenever we cook food, to know if the cook is properly cooked, what do? We just take a sample of food, and then we can say whether the food is cooked or not. Yeah. That's what we basically do in diagnostic. We try to infer the property or the quality of or the health of the beam in a particle accelerator, and then deduce our conclusion based on that. And why is beam diagnostic important? Because all over the world, particle accelerators are developing constantly, and it's growing worldwide. The different application of particle accelerators are, first is medical. You find particle accelerator in all hospitals, especially in radiotherapy, isotope production. The other application is ion implantation. So, for example, if you want to produce semiconductor chips, so you need to bombard it with ions, specific energy, which produces very intricate details inside the chip, and you need particle sources like ion sources to study them. And to study all these properties, whether the beam is in correct shape or correct size, particular energy, you need to diagnose it properly. And that's what beam diagnostics is for. Different kinds of beam diagnostic tool, different physics principles. And here I've highlighted the 4 key principles which are used in almost all kind of beam diagnostics. So first is coupling of particles, electromagnetic field. As you might know, every charged particle has its own electromagnetic field when it moves, and it interacts with its surroundings. So if your surrounding environment also has a electromagnetic field, it will interact with it. And based on that interaction, we can deduce the properties of the particles. Second is the coupling of electromagnetic field of the particle, which is separated from the particle. For example, if a particle is moving, it is also emitting radiation. And that emitted radiation also contains a very key information about particle. So if we know how to couple the radiation with the particle's properties, we can understand how particle behaves. Third is exploiting the energy deposition. So when particle is stopped, it will deposit all its energy, and it will convert all its energy and transfer all its energy in that material. And if we know how that interaction takes place, we can deduce the properties of particle. And lastly, exploiting the interaction with an external electromagnetic field. For example, if you have a magnetic field, and if a particle passes through that electromagnetic field, it will cause some variations in that magnetic field, and based on that interaction, you can deduce some property. So these are the 4 key principles based on which almost all kind of diagnostics are designed. So what do we measure? We measure particles property. And what is particle made up of? So particle, let's say a group of n particle has 6-dimensional phase space. So 3 are in position, which are given by x, y, z, and then there is momentum, which contains the velocity information of the particle. So along the accelerator length, what you have is initially you'll have a bunch of particles, and then you need at the end of the accelerator a proper size of beam. And in between, it will undergo different kinds of components. It will undergo focusing, defocusing, and then you want to know what is the particle property at the end for the desired purpose. So for all these properties, you need different kind of beam diagnostics, which calculate different kind of position along the accelerator, and you can know if your accelerator is functioning well. And these are all other beam properties that we measure. So first is the transverse position of particles in that bunch, x and y, and then its propagation angle, x dash, y dash. So since it's a bunch, not every bunch will be at the same location. It will be distributed in a certain function, let's say a Gaussian function. So its angle with respect to its motion axis will be different. So if we know what the average propagation angle of that particular bunch is, we can define its quality. Then the width of the particle bunch, for example, its transverse width and its longitudinal width, these can be determined using different diagnostics, and how it changes along the accelerator is very important. The divergence of the beam, how broad the beam has gotten under an effect of a particular element, that we can also diagnose. Then the emittance, as you might have already studied about emittance in previous lectures, it gives you the phase space of the bunch in a particular location, and it can define the quality of the beam, and it is very important, which I won't be covering in this lecture, but yeah, transverse emittance is very important quality. Energy and energy spread. So as particle moves along the beam line, it loses or gains energy depending on the component it goes through. And how monoenergetic your beam is very important to know, or how much is the spread in that energy. Bunch length, so in case of time varying beams, you need to know how fast the particle moves of a particular bunch. And lastly, the charge, how many particles are left inside the bunch as it transfers, transverses through the entire particle. So let's start with the first, let's start with the first diagnostic, measuring the beam position. So we want to know how, with respect to axis, what the bunch is going through as it moves along the accelerator. So the first and most important diagnostic, which is used in most of the accelerator, are called BPMs, beam position monitor. And they are, so here I'm showing you a bunch of particle which is moving along the pipe. So as it moves, it also has its own electric field. Since it is a conducting pipe, it will also create a charge, an image charge, which is opposite to the charge of the particle. So this will be very similar to what the particle is behaving inside. And based on this image charge, we can infer the quality of the beam. So if it is a Gaussian, we can say that the image charge will also be Gaussian, but then you have to apply some correlation between these two so that you can infer the quality of beam. So based on this principle, we make devices known as pickups. Pickups are the devices which measure the proximity of the electric field. So imagine you have two metallic plates and you have a bunch, and then you have connected it to some external measuring device which is bounded. So based on the behavior of this particle, it will induce electric field in both of these plates, and then based on the timing of each of the current or signal you have collected, you can infer the quality of the beam. So this is a typical schematic. Here you see this is the beam and this is a pickup. So pickups are usually a set of electrodes. So this is the longitudinal view. If you see it from the front, it is like this. Usually you have 4 electrodes, so each will measure independently its own signal. And depending on the position of the entire bunch, so let's say this is your axis, and if it is perfectly centered, all the electrodes will measure equally. But let's say if your beam is slightly off center, let's say if it is like this, then this electrode will feel more electric field compared to this. Then there will be an asymmetry in these 2 electrodes as well. So based on some mathematical relationship that you can calculate on paper, you can estimate the position of its centroid, of the centroid of the bunch. And if you have multiple such pickups around the accelerator length, what you can do is, let's say if this is your accelerator, and if you have beam position monitor at some limited amount of intervals, what you can actually do is you can track the, so let's say you measure position which is exactly at the center here, and if it is slightly offside here, you can reconstruct basically the entire path of the centroid of your bunch. And this is principle based on capacitive pickup. There is also an inductive pickup, since moving particle also creates magnetic field. You can basically capture the magnetic field of moving charged particle using similar devices, and then you can also infer similar qualities. This is an equivalent circuit of a pickup. So this is the load resistor, and this is the capacitance which is caused between this and the grounded pipe, the pickup and the grounded pipe. And then you can use circuit laws to find the impedance of this entire circuit. So an important and the most challenging part is to optimize the impedance, to match the impedance of this capacitive pickup with these load wires. So usually these wires are 50 ohm, and you have to match the impedance of this entire your beam position monitor with the transferring wire, because if you don't match it properly, there will be reflections in the signal and it causes errors in your measurement. And this is a typical example of pickup which I took from a book by Peter Strel. And it has this segmented aperture, so you can have multiple segments. So here I've shown you 4. If you have multiple, you can more precisely calculate the position of your centroid of the beam. The next thing is beam profile. So we already know the position where it is, but we also want to now know how it is distributed in both x and y directions. So what you do is you measure the profiles in both the direction. Usually beams are Gaussian in particle accelerator, because even if you start with, let's say, perfectly circular beam, under the influence of different kinds of forces, they distort the beam. And sometimes it does not even remain Gaussian. It changes its shape drastically, and then it can cause different losses. So different kinds of devices are used to measure these cross-section, which can be helpful in telling the quality of the beam. So, as I already said, the width is described by Gaussian. So here you can see typical profile of a beam in both X and Y, which is Gaussian. It is like a perfect Gaussian beam, but the width are different in both X and Y. So it's an ellipse, but the distribution of intensity is a bit Gaussian. And we define the width as 4 sigma. So if you have a Gaussian function, so 4 sigma, so sigma is the width, full width at half maximum, and then 4 sigma is the width which contains almost 90 to 99% of the particles. And how do we measure beam profile? We have different kinds of devices. So the first one is scintillation screen. It is the most straightforward device which you can use to measure the profile. What it is a material which is emitting light when it interacts with particles. So usually quartz is the most commonly used material, and you can view the light which is emitted through a window, and you can use the same window by emitting light and then calibrating it with the camera. So here you have your camera, CCD camera, and when a beam interacts, it will emit light in a particular angle, and then you take the image of that light, and then you can tell the width and the size of the beam. Usually these scintillating screens are kept at 45 degrees with respect to the beam axis. Any guesses why it's 45 degrees? Why not 60? Why not 30? And it will be in coming slides. You will usually see we only keep it at 45 degrees. Do you know? Can you guess it from this figure? I think it should be straightforward. So let's say this is your beam, and your check. This is 45. Yeah. If you keep it, that's it, and you are imaging, and let's say this is the beam, and you are imaging the light which is emitted in this direction. So if it is 45, your beam size that you measure is changed by a factor of √2, because if you see this length, it is slightly longer than the beam size. Yeah, and if you further reduce it, you will lose some of your beam. Yeah? So that part is not desired. And if you make it, let's say, more, then also you will lose, because more beam will interact with the material. So 45 is like an optimum angle, which gives you a compromise between the loss and the measurement. And it is only used for very low intensity beam, since it is a destructive device and you are destroying the entire beam as you are putting the entire scintillation screen in front of the beam. So this is a typical viewing screen that you can see. So you view your beam from this, and this is your viewing screen, and then you can use electromagnets to lift this in and out of your beam line. And the thing is, the light which is emitted, it depends on the type of material that you are using. Yeah? So, and the wavelength is also in optical region. So 300 to 700, which is like visible region. And the more material it interacts with, the more light is emitted. So these are the properties that a material should have. And the other properties of the scintillating material is high energy efficiency to conversion to light. So even for a small amount of interaction, it should give you more light so that you can deduce more properties of the beam. And you need good linearity between the particle flux. So let's say if you have 10 particles of electrons incidenting on the target, it should give you in proportion to the light output should be in proportion to the amount of incident particles. So you can make very good correlations. No absorption of emitted light in the bulk material, which is important, otherwise you'll lose information about the beam if beam is absorbed within the material. high radiation hardness. This is important because you are operating it continuously under different radiation condition. It can interact with material and produce, let's say, gamma rays. And when gamma rays interact with devices, they generally crumble because radiation hardness is an important issue. And good mechanical and thermal properties. Because it is constantly being bombarded with very high energy particles, it undergoes thermal loads. So such thermal loads the material should be very resilient with such thermal loads. So this is an example. Let's say you have a 1 microampere of proton beam with a spot size of 1 mm. And you are given a material which emits 24 photons per keV of energy which is being dumped. And your energy per proton in the bunch is 1 mega electron volt, for example. So you want to calculate what is the photon density. So what you do first is estimate the number of protons in 1 microamp, which is just divided by E, which is the electronic charge. You get your number of protons which are being incident on the target per second. Then you estimate the number of total energy deposited on the target. So you have the total protons per second, and in 1 proton you have 1 MeV energy. So total energy is this much EV per second. And now, since you already know the scintillation yield of the material, how many photons will you produce per keV, and you already know the rate at which you are depositing energy. So multiplying these two numbers will give you number of photons per second. And then dividing it by the spot size or the area which interacts, which is pi r square, you can estimate the total photon density. So these kind of calculation can help you estimate the material that you need for a particular, let's say, proton beam. And based on your camera which you have and how much photons it can detect, you can estimate what kind of material, scintillation material you need to use. So these kind of calculation we do whenever we want to buy, let's say, some scintillating screen or some other kind of materials. Okay, the next thing is transition radiation, specifically optical transition radiation, because it is in the optical range, we can see it, but there are other transition radiation which are not in optical range. These kind of radiation occur when the particle travels from one dielectric medium which has one dielectric constant to another dielectric constant. And this is very special because the radiation that is emitted is independent of the thickness of the material. So you can have maybe a thick screen, but and also it is emitted in a specific conical angle in forward and both forwards and backward direction. And another important thing is the light which is emitted. It depends on the beam energy. So if your beam energy is high, it will depend on that. And so this is again your screen or material which emits transition radiation. So again, you have 45-degree angle to capture most of the beam and then deflect the light. So the thing about what makes transition radiation special is the transition radiation and its angle at which it emerges. It depends on the velocity or the energy of the beam, gamma. And an approximation is that theta, which is this angle, is proportional to 1 by gamma. So the angle at which the light will be emitted, you can calculate beforehand before putting your camera at a particular angle. But this can cause a problem if your beam is a bit larger, because as you see in this angle you have these two lobes which are from the optical transition radiation. But if your beam is large, this lobe will be outside the range of your camera and you cannot capture it. So what it does is, if you plot the theta versus intensity curve of a particular beam energy, it will give you, for a particular angle, it will have maximum intensity, and for some angle, it will have 0. And then again, so it will give you this very typical M-shaped curve, and this contains the information of the divergence of the beam. So because it is a convolution of different kind of Gaussian curves, and then mathematically you can estimate how much is the beam's divergence, and then you can estimate different kinds of things. You can estimate beam's energy because it is inversely proportional to 1 by gamma. So if you know the angle at which it is coming out, you can calculate the energy of the beam. So now we measure beam charge. So any questions still here or doubts? Okay. Now we measure the beam charge and current. And this is one of my favorite things to do because I've worked on these devices for quite a long time. So Faraday cups. Faraday cups are very simple devices. It is basically a charge plate which you put in the path of the beam and then measure the amount of charge which is deposited on it. And it is used in different, not only in particle accelerator, but also in different devices like mass spectrometry, material studies, even in space propulsion. So what it is it's a metallic conductor, and the beam enters from the left. It interacts with the material because the energy of the beam is high and the work function is low. It will emit secondary electrons from the surface, and these secondary electrons, depending on the design of Faraday cup, they will either escape or go back to the surface. But the challenge is confining these secondary electrons. So what is the issue? Here are two cases. The first case is the secondary electrons which are escaping the Faraday cup surface. And the second case in which they are not. So imagine you have a Faraday cup, which is just a plate of a metallic material, and you have a current measuring device, and this is grounded. If you have let's say 5 coulomb of charge coming towards the Faraday cup, and since it is grounded, the total charge on Faraday cup is 0, and you want to measure a 5 coulomb through a Faraday cup. It gets deposited on the surface. So now this entire thing is at 5 coulomb, yeah. And since it is grounded, the current will flow in this direction, and you measure 5 coulomb here. So it's perfect device, yeah. But the problem occurs when the beam energy is very high. So again, the same case, but now a different scenario. It is 5 coulomb, but let's say its energy is very high. So it comes, it interacts, and this kind of situation occurs in which electrons are emitted. Let's say the electrons which are emitted are of carry 3 coulomb charge, yeah. So initially this was at 0, but since it has lost -3 coulomb of electrons, so its total charge will be increased, yeah. So it is now at +3 because it is losing -3, so its total charge is +3. And the 5 coulomb which comes, it is also added to it. So in the end, you are measuring an extra charge of these 3. Unless you suppress them back to the surface, you'll measure an excess of charge in your measuring device. If it is a negative charge, you will underestimate the current. If it is a positive charge, you will overestimate the current. So the trick is how to suppress this secondary electrons which are emitted through the interaction of high energetic beam. What you do is you put a ring in front of a metallic ring which is isolated from this, and then you apply a negative potential to it. Let's say minus 100 volt, because these secondary electrons which are emitted, they are not of very high energy. The typical distribution is which peaks at around few tens of EV. So you may not need very high voltage, but there are some tails of this distribution which can emit and lose. So if you really want to measure, let's say nanoampere level of current, you need to apply very high voltage. And then a typical way of calibrating Faraday cup is shown in this plot. So what you do is you measure the Faraday cup, current measured in the Faraday cup, and what is the actual beam current that you expect. Yeah, you can measure it with another kind of diagnostics, which you already know. And you vary the repeller voltage or the suppressor voltage. So this is the suppressor voltage. So what you can see when you do not have any kind of suppression, when it is zero, obviously you'll measure very high current because all your electrons are being lost. But as you start decreasing its, as you start increasing its potential, making it more and more negative, what you see is these electrons are getting repelled back to the surface and they are not escaping. So ideally, your actual current, the ratio of your actual current and the current measured by Faraday cup becomes 1, which shows you that you are actually measuring the actual beam current. So typically, we do this thing to calibrate our Faraday cup. We change the suppressor voltage, and then once it becomes constant, we usually keep it at the minimum value at which it becomes constant. So usually between the range of 200, 300 volts, it's enough to suppress the Faraday cup. This is one of the methods of suppressing electrons. There are other methods in which instead of electrostatic, you use magnetic fields. So let's say if you have a permanent magnet in front of the Faraday cup, it will create a transverse magnetic field, which will also trap the electrons which are being emitted. It won't affect your incoming particle because it is very high energy, and it will cause the same effect. So both electrostatic and magnetic suppression are possible. Another method is if you make your Faraday cup longer. Let's say sometimes you do not have enough space. That's why you need short Faraday cup. The width of the Faraday cup is short, so you need to make short. But let's say if you have enough space, and if you make it very long, and then you may not need any of these two methods. So if your incoming particle strikes the surface, it will create secondary electrons. But these secondary electrons their geometric path length to escape the surface is increased by increasing the length. So eventually they will be recaptured by the surface of the Faraday cup. So this is a very common device used in all kind of particle accelerators. The challenging part, another challenging part is when you go to very high energies and high powers. So let's say, this is an example from one of my own works, a Faraday cup which I designed for a neutron beam for an accelerator-based neutron source. So what happens is, in this case, you see the requirements were very stringent. We needed a 300 kV neutron beam and a 30 milliampere of beam current. So if you estimate total power based just on this energy and current, it's around 9 kilowatt, which is very high for such a small size. So you cannot cool this kind of power just by keeping it there, because these devices work in vacuum, and in vacuum you do not have conduction. So the only way it can cool itself is through radiation, and 9 kilowatt is very high. In simulations you can see if you keep this load for very long, it will surpass its melting point. So what you need is a cooling mechanism. So what I did in this case, using the CFD simulation in ANSYS, you can design a cooling jacket around it. It's a cooling tube made from copper, and then using different flow rate of water inside these pipes, you can see the effect of how much the temperature rise occurs at the place where beam interacts with the Faraday cup. The material depends on your application. Usually the Faraday cups are made of copper because copper is conductive, it is easy to manufacture, easy to machine, but then depending on your application you can change the material. And also the cooling water is another thing, because let's say for 30 milliampere it's not a big problem because it is too high of a current, but let's say if you're measuring the current in the order of nanoamperes, even the cooling water can carry away some current through it. So it is very important to use demineralized water we call it DM water, which does not have any salts in it, so it does not provide any conducting path for the charges to go through. And the other application of Faraday cups, as I told in my introductory slides, they are also used in ion thrusters, sputtering application. Especially for ion thrusters and surface modification, you have very big beams. So typically for accelerator, you have beam sizes of few mm, but for ion sources which have application in ion thrusters, they are typically 5 centimeter, 10 centimeter beam. So what you use it for is measuring the entire beam profile. So let's say if this is your ion source and the beam is like this big, there are two ways in which you can measure the beam profile. One is either you use single Faraday cup and you move across the beam, and then it will give you a Gaussian profile, because it is Gaussian because here you measure less intensity, and as you go towards the center, your intensity will increase, and at the end it will reduce again. Or you can do is you can have an array of Faraday cups. So you can have multiple Faraday cups across the beam, and then each will independently measure its profile, and that's what I did. I designed this Faraday cup array. So each hole has a Faraday cup inside, which is made up of copper, and then for this you also need to use different kinds of codes. So this is tracking simulation, which I did it in CST Studio. So you define a source, and then by applying different kinds of negative voltages, you see how the particles are deflected. So this is for the electrons which are deflected. And also, usually the Faraday cups that we use in particle accelerator, they are at ground potential. But it is not always the case. Sometimes, depending on the application, for example, this Faraday cup, which is from this paper, this has a typical design in which Faraday cup is kept at positive potential. Why? Because in ion thruster, you have a lot of charge exchange ions, which are very low energy ions. And when you measure the beam profile, you don't need slow energy ions. And to repel these slow energy ions, you slightly bias it positively so that it repels all the slow energy ions, and only measure the fast ions, so that you can get a pure profile of fast moving ions. Other challenges, material sputtering. So as I said, that as it interacts with the material, it will sputter material. So the material will come out, and due to sputtering, what happens is, since this is isolated, so you use some kind of alumina ceramic to isolate, and this is at very high voltage, let's say minus 500 volt. But sputtering can also cause deposition on these kind of ceramic which are used for isolating, and with time, as the material deposits on the electrode, chances are there it will create a conducting path through this ceramic, and this causes errors in your measurement. So you are applying, let's say, 500 volts, but actually you get more voltage because it has become conducting. Then electromagnetic interferences. For accelerators which operate in, let's say, RF regimes, you always have electromagnetic waves traveling through and fro. And if your measurement device is not properly isolated using different kind of shielding mechanism, then you'll have these kinds of issue. Faraday cups are also used, as I initially said, that in mass spectrometry, and mass spectrometry also uses isotope separation, radioactive isotopes. And because they are deposited on Faraday cup material, they causes the activation of material, and you have to be careful to estimate the amount of activity remaining in the Faraday cup once you irradiate with a radioactive beam. And the last and the most challenging part is to design Faraday cups for antimatter beams, because antimatter is a big challenge to detect with the normal matter thing, because whenever it will come in contact with your normal material, which is like Faraday cup, it will create highly energetic annihilation fragments. And these energetic fragments, so let's say if an antiproton beam comes, it interacts with this, it will create charge pions, or maybe let's say some annihilation product. Usually annihilation products are heavier, so they will deposit and they don't carry a lot of energy. But charge pions are lighter and they shoot with very high energies, for which you have not designed this Faraday cup, because it is only to suppress the secondary electron. But these charge pions, they escape at, let's say, MeV of energy, and you cannot stop them. So that's another challenge. I'm also right now working on some kind of design of these kind of Faraday cup, and yeah, let's see if it works out. Any questions still on Faraday cups? Yeah. Now we come to losses. So we have measured charge, we have measured position. Now we measure losses along the beam. So under different kind of forces, beam contracts, beam expands, and some particles are lost. So what kind of losses we expect? We can directly detect the particles which are lost from the beam, which is like direct detection. So let's say if there is a bending magnet there, and if you expect some particles are lost, you just measure the loss of the particles by different kinds of mechanism. And then there is detection of particles, indirect detection of particles. So let's say if the particle interacts with the material through which it goes through, then it will create activation in that material, and then it will create a secondary kind of particles. So one of them is Bremsstrahlung. Let's say if a particle is decelerated, it will create Bremsstrahlung radiation, and it is usually for electrons, it is above 100 MeV. And then the second kind of thing is fragmentation, which I already told you, and fission for heavy ions, which are very heavy, like let's say uranium. They can be fragmented into lower mass particles, or it may lead to fission, which causes the production of radioactive nuclei and the emission of fast protons. So you detect these kind of particles like fast protons and neutrons, and you can tell what particles are lost from the beam. So one of the most common devices for measuring losses are called ionization chambers. And they are used basically for machine protection, because you don't want losses in your beam, because if these high energetic particles are lost, they interact with your electronic circuits, they damage it, they damage your accelerators anyway. So how do you detect them? So ionization chambers are the most common one. It's basically a gas field detector. So you have a chamber which is filled with a pressurized inert gas, usually it's nitrogen, to keep the environment clean so that it does not interact with any other material. And then you have two parallel plates. So one is cathode, which is at, let's say, some negative voltage, and the other is anode, which is a positive voltage. So it creates an electric field. So this is the direction of your electric field. And let's say your accelerator is somewhere here, and there are some losses which emit gamma. And this gamma, when it passes through this, since it is a pressurized gas, it will interact with the gas molecules, and then it will create electron and ion pairs. So because this is gas, this is very high energy, and it will create an electron pair and ion pair. So these will move in opposite directions. So ions will move towards cathode, electrons towards anode, and this will create a current in the external circuit. And then you measure the current, and based on the calibration that you use, you can tell the kind of particles that you have detected, its properties, and all of those stuff. The most important part of this is the electric field, which has to be kept sufficiently high. Can you guess why we should keep it very high? Any guesses? Why not a normal electric field? Why we need a high electric field? The basic reason is because, let's say, if the electric field is not very high, you give enough time for these electrons again to combine with your ion, and recombination occurs, and it again becomes your neutral gas. So it does not have enough time to reach anode, and before that it becomes a gas. So you lose your measurement. So if it is very high, all these electrons move very fast towards the anode without getting recombined. That's why you need a very high electric field. Plus, it is also kept under high pressure. So here you can see the gas, which is nitrogen, which is kept at 1 bar pressure. Pressure is also kept high to increase its interaction probability. So you have more dense gas inside the chamber, so your interaction probability also increases. So these are called pressurized loss monitors, but the same principle is used in smoke detectors, which we have in buildings. So the smoke detectors has a similar principle. It continuously emits alpha radiation. When it encounters smoke in between, it changes the current because of the gas, because of the attenuation. So the working principle is the same, but yeah, different applications. Now, the problem with beam loss monitor is they are kept at specific intervals. You cannot keep like a line of beam loss monitor because they are bulky, and it's practically infeasible to keep it along the entire length of your accelerator. Yeah, let's say if your accelerator is 1 kilometer long, to make 1 kilometer long beam loss monitor, it's a very expensive thing. So another kind of technique or solution to these kind of issue is using Cherenkov radiation. Anybody knows Cherenkov radiation?
Where electrons move faster than light in a certain
medium. Yeah, exactly. So it happens when a particle travels at a speed faster than the speed of light in particular medium, and it emits typical radiation, which is called Cherenkov radiation. So what we do here is, instead of using ionization chambers, you use optical fibers. So let's say this is your accelerator, and your particle beam moves, and let's say here are some losses which produces secondary particles, electrons or ions, whatever it is released. So what you do is you have an optical fiber which runs along the accelerator length, and when it goes through this fiber, it will produce Cherenkov radiation. You choose such kind of material that it causes Cherenkov, and then since it is an optical fiber, total internal reflection will always take place, and this signal will reach the end of the fiber. And at the end of the fiber, you have devices like for detecting this signal, and then it converts it into electric signal using, let's say, photomultiplier tube, PMTs. And then what you do is you measure the time it requires for this light to reach your detector. So it will give you a typical time versus intensity curve. So it will give you a time of flight curve. You do it the same in the opposite direction. And based on this time of flight, you can be sure that, let's say, if this length is smaller, it will reach this distance faster. And if this length is larger, it will reach this distance in a smaller length. So based on these two times, you can exactly pinpoint where your losses occur. So this gives you a resolution. Theoretically, you can achieve it within 0.5 meters. And we have employed these kind of detectors in experiments. So let's consider a numerical example. You have a 1 GeV electron which passes through silica optical fiber, which has a refractive index of 1.46. So let's say if it's a 50 meter length, we have to estimate its time of flight. So the first condition that we need to see whether it will produce Cherenkov or not. So what we do is we estimate the speed of light in optical fiber. So this is the simple relationship, dividing it by its refractive index. You can estimate its speed of light, and then you compare it with the speed of light for 1 GeV electrons, which is around 2.99, which is relativistic. So obviously it is larger than this, and it will produce Cherenkov light. And then to estimate time of flight, you just divide the length by the velocity of the light in optical fiber, which is 244 nanoseconds. So here we have estimated the time of flight, given that we are given the length. But in experiment, what we do is we measure the time of flight, and then we estimate the location. So this is a typical experimental plot of a particular. So these are two different fibers. So it tells you the distance at which loss has occurred. So there is one fiber at the top, one fiber at the bottom. So the first loss occurs at this location, second is this, and the third is this. So these can help you identify non-destructively, which is very important, and non-invasively. You are not invading, you are not going inside the particle beam to know where the losses have occurred. This bump, which you see at the end, is just the reflection, because light can be reflected back and it can cause some errors, but it is not important for us. So yeah, so Cherenkov and optical beam loss monitors is like one of the very new kind of diagnostics which we are using in our group as well for monitoring the losses along the accelerator's beam line. Now, antimatter diagnostics. This is my also area of research. I work with antimatter at CERN. So the collaboration that I work is called the Aegis collaboration, and we want to measure the effect of gravity on anti-hydrogen atoms. And we use different kind of diagnostic tools to measure the properties of antimatter atoms. So the first and the most commonly used diagnostic which we use is called the MCP, or called microchannel plate, which is just it's just a plate which consists of multiple channels, which let's say the thickness of each plate is very less, of the order of few mm, and then you have these channels which are etched using some beam machining method, and then when the particle, let's say an electron, interacts, it undergoes multiplication, and then you image it on a screen, and then you can get the entire image of your particle. So this is a typical example of typical antimatter plasma, which is very characteristic. On left you see antiprotons, which forms this hollow ring, and here you see electrons. And why it forms is when you mix electrons with antiprotons, usually in the experiment that we use antiprotons, they come from CERN's larger accelerator, and then we stepwise cool it down. And to cool it down to further, let's say 55 Kelvin, because we need such cold antiprotons to make antihydrogen. What we use is we use electrons. So we make a soup of electrons and antiprotons, and then since it's a mixture, let's say one of them is at a high temperature and one is at low. Let's say one is at 1 eV and the other is at 1.5 eV. If you mix them together with time, they will come in thermal equilibrium with each other, and both of them will have almost the same temperature. But since antimatter is trapped using both electric and magnetic field, so let's say this is the magnetic field, they have this rotational motion along the magnetic field line. And since antiprotons are heavier, they experience a centrifugal force outwards and form this kind of ring structure. And that's how you identify the temperature of antiprotons based on the size of the ring and all the other properties. So antiprotons, okay, you can detect it using this. Antihydrogen have another way of detection. We use scintillation materials, like scintillation fibers. So this is a typical scintillation fiber bundle which we have in AGES experiments. So it has different kind of layers of scintillating fiber. So imagine this is the core of the experiment, and then on the outer you have the entire thing covered with these kind of scintillation detectors. And each has a different layer. So there are multiple layers which help in detecting anti-hydrogen. So this is the cross-sectional view. So how do we detect anti-hydrogen or anti-proton? So as you know, when they annihilate or when they touch any material, they create these charged and high energetic pions. So let's say if annihilation, and let's imagine this is an electrode which is used to trap antiproton, and it touches the surface, it will create very high energetic pions at a particular angle. So depending upon the energy of annihilation, the particles are released, and they have a certain angle at which they will be released. So what we do is we know the math, what angle and what particle and what energy it should come out. And since it has different kind of layers, we know the timing at which it crosses each layer. So with these things, we can reconstruct and we can know where the particle was formed. So the indirect way of detecting antiproton or antihydrogen is whenever the first step is data collection. So the first step is we collect all the data. So these all fibers then are connected to your amplifiers and digital signal, and it will give you like a time of each signal detection. So this is time, and this is the intensity at which it is detected. And you have these kind of signals for different layers. So what you do is you collect all these data, and then you group them. So different channels, you group them in different paths, and based on the time at which they arrive, you construct and reconstruct the path of each particle. Then again, since there are like errors because of the magnetic field, there can be some stray data which can corrupt your measurement. So you use statistical techniques to filter out outliners in your data. You don't you reject all the paths which are not very reliable or which don't appear very natural in your data. So once you have all these, once you have ruled out all the possibilities, so all the probable paths that you have, you use mathematical techniques to reconstruct the original vertex at which the annihilation must have occurred. And that's how you detect the particles. You have to do it iteratively because it is very intensive process, so you need a lot of data. Right now people are using machine learning algorithms, especially in big detectors like CERN, CMS or ATLAS, where billions of collisions occurs per second, and you have petabytes of data, and to reconstruct it within the detector, it's a huge computationally intensive task. So, and for smaller experiments, it is okay, we can do it in a normal computer, but it is still challenging depending on the kind of things that we do. So yeah, that's the lecture. And if you want references, I highly recommend, especially for antimatter detectors, Alexandra Gligorova's presentation, which you can find it online. And these are all the references which I have used for making these slides. Any questions? What are your interests in physics? Do you like accelerators, particle physics? Particle physics.
Quantum theory.
Nice. Cool. Thank you very much.